So thanks for the introduction and the invites of this talk. Today, me and Shanwen Li will jointly present this work on MetaCLIP 2, a worldwide scaling recipe. We are research scientists from FAIR at Meta. We are working on fundamental data research, and we kind of leading the MetaCLIP and the ViT-H and several big foundational research work at Meta that contributing to the many big projects at Meta, like Llama, Dino, Perception Encoder, Web SSL, and Smart Glass, and so on. So our research philosophy is kind of building everything from scratch without much external dependency. And we want to focus on funding and identify bottlenecks along the pipelines of research and make things scalable and be open to the research community. This is our team on MetaCLIP 2. So we have.
Sorry for interruption. I think you are in presenting mode, but we can only see the keynote slide.
You mean, okay. So how should we?
Can you present again?
Yeah. I don't know how to. If I'm in presenting mode, I'm out of control of this window. I don't know how to make this window in presenting mode, I guess. Let's see.
Yeah, could you full screen this? So it's like we are only seeing a short window in the middle right now. A small rectangle that has the
like make this go bigger.
Yeah.
Or you can the view button at the top. At the top left, there's a view button at the top left.
Your voice is a bit choppy.
Yeah, Benedict, your voice is a bit choppy. Yeah, I think so. There's a top left. There's a view button. You can go there and.
Yeah, it's audio setting. Yeah, I didn't much. Is this sounds better?
Yeah. I think so. This is good.
Yeah, I will be closer to the microphone. So, yeah, assuming we can present with this window without full screen mode. Okay, so this is our team on MetaCLIP 2. We have 16 people altogether from core team members and also advisors. So before we start, I'd like to share our motivation on this talk. We want to share our observations and insights on data with the community, and so to encourage people to have more discussion and driving more people into this area. And we also want to explain why MetaCLIP our data in general and very important foundation for many big projects such as multimodal language model, image segmentation, vision encoding, video generation, and recommendation. So the outline of the talk is we want to start from something that is people often talk about, like scaling and data, but move on to more insights of what's actually running behind all of these two important terms. And we also then will move to the MetaCLIP 1, which is the core backbone for MetaCLIP 2. Then we switch to MetaCLIP 2 with more technical details. And lastly, we want to make future prediction or estimation about what's next for scaling and data. So let's begin with the scaling and the data parts. We know that everyone nowadays talking about scaling, and we know we pure a lot of compute data and the bigger models, we get better performance. But what actually works behind scaling is not very clear on the surface. So we'd like to share our observations on scaling is that because scaling enlarges the scope of the data, it gets more diverse experience and also broader scope for the optimizer or model training to look at, so for better generalization. And of course, bigger model enables bigger possibilities of discovering hidden and emergent higher order structures, such as from really raw low-level data like physical world data to maybe more abstract laws of governing the physical world to more maybe more abstract concepts in human beings like philosophy and so on. So we like to share that all these higher order underlying the governing this process, kinds of governing the underlying fundamental laws and the process that dictate the rise, transform, and falling of all things. And of course, we also facing some resource limitations. So scaling is never free. Each step of the scaling brings new bottleneck. We cannot scale arbitrarily. Because of the limitation, I'd like to share the famous kind of theory called shortest plank theory, mostly found in system optimization. And so if we want to optimize the system, we always have to find the limits or the hidden bottlenecks of the whole system. So if we improve that bottleneck, we can get the whole system improved. And taking transportation for example, if we start imagine people taking horse for transportation many years ago, the scaling capability is very limited. It's bottlenecked by the animal-powered horse legs, right? And we cannot easily scale that to much larger scale, and also the maintenance of the horse is expensive, right? And so by inventing the car, we actually unlock the possibilities. And from horse to car, the scaling is not just about scaling legs, but totally reinventing the whole system, building 4 wheels for the car, and also correspondingly paving the roads for the car, so that the scale is much bigger than the legs for horses, right? And by doing so, people can have more diverse experiments throughout the day, from daily work to travel, which is a much bigger scope than riding a horse or even working several hundred years ago, for example. So next, I'd like to move on to how AI scaling is about. And taking for example, the SVM, for example, they are popular before late 2000s. And at that era, people usually talking about big data, but small model. At that time, the bottleneck is the small model. The real bottleneck in the model is the fixed nonlinear kernel in SVM. Because it's fixed nonlinear, the model says you cannot grow too much like the neural nets works nowadays people are familiar with. And then after since the 2012's AlexNet breakthrough, we unlock the possibility of scaling the models. Now, since the model keeps growing, and probably it's the stacks of learnable nonlinear transformation with much bigger capacity than the data's information can supply. Now seems the data might be the new bottleneck. If we talk about data, we may first imagine the bottleneck could be the data volume. And in the context of this talk, we are more focusing on data filters because data filters are of course limit the size or scope of the data. And also data filters are more likely human-made bottlenecks, which if you know Richard Sutton's term is called beta lesson, which are essentially the human-made bottlenecks of the whole system. Then if we remove them, we get those unlocked. But those human-made bottlenecks are usually very hidden or implicit, so it's hard to discover at the very beginning. And let's talk more about the definition or details of the data. Before we start, I'd like to share that data is something that everyone talks about. Nobody really knows about how to. Everyone thinks everyone else is doing it, so everyone claims they are doing it. There are many, many terms nowadays like that people are really familiar with, but we don't really make much progress on it. And everyone claims they are using it and doing it. And this is the statement back in 2013, but it's still valid nowadays for data, I guess. And in 2025, maybe the recent more popular terms, the AGI, which may also applicable in such situation. So we really want to share our insights on what's about data and how it's generated from and what's underlying happening and so on. So imagine this dotted line is a history of humans or in general agents' activities. At some point, we observe an image, for example, a frame of handwritten digit. And later, someone, like some annotators, label it as 0 in natural language, or maybe someone found it's called 0. What is important is that there are some underlying labeling and recognition process in between these two time steps. And running goes from one observation to another. And they are mostly hidden. We don't know what really happens in between them, like how human observe each pixel and find it's actually 0. And so we use machine learning to kind of approximate such hidden process and generalize across many similar process. We build a machine learning model that captures the structure in these unknown processes. And notably, not every process is equally valuable. For example, if we go back to a few frames before the previous 0, there could be no change, right? If two observations have no change, then they have much less value. And in our common terms, it's called maybe low quality data also. And so the scaling is more about finding more observations with diverse change. That's our observation on what scaling on data is really about. And so after that, we'd like to show the history of the whole scope of the image data curations in computer vision domain, and how people's skills from both visual concepts and image volume over time. It starts with ImageNet, which covers about 1K to 21K visual concepts with a data set at millions or maybe 10 million scale. Then it comes to CLIP, which scales up to 400 million image text pairs, representing about 500K visual concepts mined from the web. After that, we kind of scaling the English word data. For example, in our MetaCLIP 1, we aim to exhaust the English word data in Common Core and pushing the volume of data to billion scale. And in MetaCLIP 2, in this work, we kind of scaling the visual concepts to 27 million visual concepts, and also doubled the image volume, pushing image curation into truly global and diverse territory. One thing to note that is the truly important moments is how we switch from one stage to the next. It's less important about how we scale the compute and storage to improve the skill within each stage. And so the key research efforts is to identify the hidden bottlenecks and break through them and make the research scale to the next level to enjoy the scale of the larger and diverse experience and the capacity. For example, from ImageNet to CLIP, we can now break the size of the visual concepts from word9 to 500K visual concepts. And from CLIP to English word data, we kind of scaling the data pool size. And also in MetaCLIP 1, we kind of open the method that is described in CLIP into a formal algorithm that fully makes the scaling happen on much larger data pool. And in MetaCLIP 2, we kind of breaking the limitation of English visual concepts from 500K to 27 million visual concepts, and also correspondingly break the training scale and double the data volumes to enable the worldwide data and better performance than the English-only model. So we do expect some new limitations or bottlenecks at this stage, and we encourage the community to discover new bottlenecks and move the scaling to the next level. And we'd like to also share some our estimation in the end of this talk. So next, I'd like to revisit the MetaCLIP 1 and inspect how we find the bottleneck and break the limitations. MetaCLIP 1 scales up the clips 400 million image test pairs to cover all English word data in Common Crawl. This was made possible by formalizing a data curation algorithm that scales data and control the training distribution at massive scale. The beauty of this algorithm is it's very flexible and scalable. It can be easily plugged into a traditional data pipeline and improve the data throughput. Along the way, we examine well-known filters and find all of those filters are probably unnecessary or even harmful, like clip filters, file name filters, and date filters. So we kind of follow the clips philosophy on no filter philosophy, that we only do data selection or curation, never do filter, because the filter may implicitly place some human-made bottlenecks along the pipeline that initially you may get some performance gains, later it becomes a hidden bottleneck. And in MetaCLIP 1, we also make the online curation possible, that it's training on distribution. We can demote the concepts of a finite data set that you can iterate many, many times, for example. And to start, I think MetaCLIP 1 this is our starting points, which kind of a short description in the original CLIP paper. It's kind of a search engine powered process, and MetaCLIP 1 is kind of turning such process into a simple algorithm into just a two-stage of running. So the original description is kind of searching the internet image test pairs and matching them with 500K queries, and lastly balancing them. We kind of put everything into these few lines of algorithm. We first do substring matching, and we do the global count, and later we balance the substring match the data with the global count. Associate each data example with a sampling probability. The key part is that we minimize the global operations in this algorithm so that can be easily scaled in a traditional data pipeline. And if we sort the visual concepts counted with substring matched data examples from tail to head, we can find the MetaCLIP data algorithm kind of heavily reduce the head distribution during the balancing stage from exponential growth to linear growth, so that the resulting purple line of training data distribution is more diverse. And such algorithm achieves both efficiency and effectiveness. Here is a plot of the ImageNet zero-shot classification during the training. We can see if we do nothing on the data, we kind of have this raw red line of performance growing. But after applying the algorithm and everything running in the training stage, it can get much faster training efficiency and also better performance. So kind of bending the training curves during training. And one case study like to share that it's the MetaCLIP algorithm is not just for CLIP training, but also the resulting data can help breaking the bottlenecks of many other related areas, such as this web SSL. I think it's presented 1 month ago at Cohere Lab, and it's also an amazing work that uses MetaCLIP data to also show that we can break the previous self-supervised learning that people assuming it may close to saturation, but in fact it's not. If you have more diverse data, you have much bigger room for self-supervised learning to improve. Okay, so next I'd like to move to MetaCLIP 2, which is the main focus of this paper and talk. Through the building the algorithm or data pipeline on MetaCLIP 1, we found that one major bottleneck is existing CLIP data curation, focusing mostly exclusively on English, and it means more than 50% of the data are immediately dropped after the initial stage of the pipeline. Such kind of things kind of serving as an implicit English filters. Having such a filter is probably by design, because if you train an English only model, you usually get better performance than you mix English and non-English training data together. For example, in mSigLIP, the English performance is worse than the English-only counterpart of SigLIP. And such performance drop, of course, hinders wide adoption of the multilingual CLIP model. So because the English use case is still the major use case. But by doing so, of course, it's not just about a filter on language, but also about filter on culture. You may miss many images that are non-English only. And if we support the no filter philosophy for CLIP, we probably also need to make this similarly applicable to languages. We should remove such language filter. So to remove this filter, we identify many bottlenecks. We carefully examine each stage of the previous MetaCLIP algorithm and pipeline, and remove the bottlenecks stage by stage, summarized in this figure. So at the very beginning, we don't have the multilingual or worldwide visual concepts, so we have to expand the visual concepts from the original 500K to right now 27 million visual concepts across the world. And they span in more than 300 languages on Wikipedia. And of course, we have no, it's not limited to those 300 languages, because we kind of design a specific other language type in the visual concepts or metadata, so that as long as the alt text or the text in the image text pair matching any of those visual concepts in other language, it still can do the matching. So there's no limitation on number of languages essentially. And also for the data algorithm, we need to scale the substring matching to all the languages covered, and also for balancing and sampling of the balanced example during training. And further, we scale the training scene pairs of the training throughput during training, we found this part is essential for breaking the previous curse of multilinguality or the English performance in mixed language training is worse than the English-only model issue. So to take a closer look of this issue, I'd like to share these plots. The blue bars are the English-only model performance. The purple bars are the worldwide or English plus non-English data performance. And the green bars are the non-English only data's performance. From the left figure, we can see that the curse of multilinguality still exists in the largest model of the in OpenAI CLIP model. For example, in the ViT-H, if we train both English only and worldwide data, the worldwide model is still worse than the English model, even though we apply all the recipes in the previous slides, except the last stage. So when we increase the model size to ViT-H, when the model capacity is large enough, we can see it has such emergent capability of discovery of shared knowledge among English and non-English, so it can break the curse. On the right figure, we also show that English data can help non-English data. So the worldwide data, or the purple bar, that makes the English and non-English data together always wins over the non-English data trained alone model. And also we are much, much better than the previous SOTA multilingual CLIP model. And the algorithm is still simple. We take the previous MetaCLIP 1's algorithm and backbone and only plug in the necessary changes for the worldwide data curation, starting from counting worldwide data on different languages to balancing and compute the balancing for each language. So all the curations are language by language. So if user wants a different combination of the languages, they can easily adjust from this algorithm. We maintain the independence among different languages, for example. And this table shows the main results of this MetaCLIP 2 research. Especially there's some ablation studies related to previous curse of multilinguality and how we break them. So for example, in the ViT-H model, we still see the curse of multilinguality happens, even though we increase the throughput of the training on worldwide model, like in the line here, it still performs worse than the English-only model. But if we scale to the ViT-H model, such curse disappears. And here we show 4 different controlled studies to show that English-only model is suboptimal, non-English-only model is also suboptimal. And if we keep the same throughput as the English model, is still suboptimal. But if we increase the throughput of the training of same pairs, we get the best performance. And this figure shows how the resulting embeddings performs compared to other models. We show both alignment and uniformity from the existing paper's measurement, and we show MetaCLIP to achieve the best performance on alignment and uniformity. The number is lower, the better on both axes. And also MetaCLIP 2 with worldwide data performs better on cultural diversity, on those zero-shot evaluation on dollar street, GLDV2, GODE, and also on few shot accuracy on geolocalization. And lastly, we like to share our estimation on future bottlenecks and probably how we can break them. And so throughout this talk, we focus on identifying the key bottlenecks along each stage. And we believe after we exhaust worldwide image text pairs, there's still few bottlenecks currently. So for example, on images, we're only using spatial complexity in those images, but the temporal changes are mostly ignored. So we guess leveraging the video data for the next stage is very important to learn something new that image-only data is not possible. And after that, we believe we cannot exhaust all maybe human collected data. Then the way human do the data collection is probably the next bottleneck. And if we can scale the mechanism of data collection and not just humans, but maybe also building some robots or even some surveillance camera that are not directly controlled by humans, we can scale the amount of data. And in general, then we can scale the data for many different types of agents. Yeah, I guess that's our current estimation. And we open source all the metadata, code, and model. Some for MetaCLIP 2 are still work in progress. And we have those websites and welcome to use. And we hope the communities work together to drive and identifying future bottlenecks and break them, make the scaling to the next level. Thank you.
So I'm curious if it's time for Q&A.
Yes, I think so. If anybody has any queries, you can just go ahead and ask the authors here. I guess I will start with the first one. So, like this, as a encoder, I think so. In vision language models, it is being used worldwide, and the curse of multilinguality is being kind of broken up. And so what do you think with the advent of this new wave of generative AI? Will this be helpful in such downstream applications? Like their applications in like generation of visual, like text to visual prompts, or like as recently Sora 2 was released, or other video generative language models. So I was thinking about the applications of them with multilingual and like trying to use different languages continuously, and the downstream applications of them.
Who do you want to take, or you want me to take first?
Maybe you can take first.
Yeah, so I think this is a very good question. We think like our effort just sets the foundations for approaching the multilinguality and the different culture, and having a good representation of them. Being a foundation models or data, I think inevitably it probably introducing some redundancy for the downstream applications. Maybe for downstream application, you only focus on certain languages or certain domains. So for different kind of use case, we do see like distillation or further model compression can be derived from this foundation model. For example, like if we take Dino as an example, like in their Dino 3, they first trained a very big, maybe 7 billion parameters model, and they further distill smaller models. And so the practitioners can have choose different size of a model based on their use cases. So we definitely see like this is a contribution of our work to build this foundation data and models, and a practitioner can further distill, and hoping to address like the curse of multilinguality and the efficiency for different kind of use cases.
Mm-hmm. Like from the paper as well, like I see that the ViT-H 14, that's the inflection point to break this curse of like the capacity of models to express and like break the curse of multilinguality. So like after this point, you kind of see the emergent behaviors like that you describe in the paper and in the results as well. So yeah, that's.
Yeah, exactly. So I think in our paper, we see the inflection point is at ViT-H. Just one thing we want to flag is because we want to have our recipe as general as possible, so our purpose is to show there is this inflection point. But we know like as the emergence of the LLMs and the multimodal research, there are actually more and more sophisticated algorithms to train this language image encoders. So we do believe, for example, mSigLIP or other recipes, they probably yield the inflection point at a smaller scale of the model size.
Yep.
And also I want to comment, because we're focusing on the bottleneck of scaling, so we make it on ViT-H where we already exhaust the English word data. Then we find the bottleneck moving forward is multilingual or worldwide data. It doesn't mean smaller scale won't happen, but more likely means the bottleneck is level by level. We first have to exhaust the English word data first, then make sure English performance should be the best. Then we move on to worldwide data.
Mm-hmm. True. Okay, then if nobody, I would like others to pitch in and ask any queries if they have. Yeah, Benedict, do you have any quick queries here? Okay. So like, where do you plan to go next? Will it be integrating this into your own pipelines inside Meta, or since you have released it and like you will be releasing the other stuff which are open source too? So where do you see this going in future, and what is the research direction for you in the next like year or so?
Who do you want to take this, or you want me to take?
Yeah, maybe better for you.
Yeah, so as at the beginning of presentation, I think we mentioned like this effort has been widely used across Meta, no matter it's for research and production use cases. So I think one important thing for us is just keep pushing these kind of adoptions, like in our Llama and the future LLMs efforts, and also in Meta, like SSL, for example, Dino, or like other representation learning models like SAM and JEPA are also very flagship projects, and we are going to keep pushing the data for those kind of efforts. And on the production side, the more conventional, for example, recommendation systems, this is also the route we want to impact as well. On the research front, we definitely see like this benefit of keep pushing the scaling. And I think MetaCLIP is an example, like we try to figure out better semantics, representations, and distributions. And there are actually more access in the vision and other areas. For example, the physical world data, the geometries, and more. So this kind of dimensions are also things we would love to keep pushing as well.
Cool. Like there are various things too, like with the VJEPA and Dino. Like I think so, there are various research avenues inside Meta that can leverage this to take this further. All right, Mohammed, did you have? Yeah.
Can you hear me, right?
Yeah.
Okay. Yeah. So I just have like a question about the last slides that you just talked, like using video data to scale like for like next generation scaling of this work. So how like do we envision using videos? Because videos are like very complicated signals. They have a lot of information in them. So like what do you envision? Like do we need think of some sort of data structure? Like do we use some sort of the state like models like JEPA, or we can envision some integration of that to enable like further scaling or like this approach? I mean, because I don't have any sense of how to use it. But yeah, it's a more general question. Yeah, anyone can answer, or both of you can answer. I mean, on if you have different opinions.
Yeah, maybe I can try to answer that. I think from our side, we are more on the focusing on the video data, not directly training the model without looking at the data carefully. So the video data is significantly from the image spatial composition, which shows you how things really changes. And for images is kind of a static results. You have a long history to formulate how the image currently look like. Like initially you have an empty place, and later you place some tables in the room, building the walls, and later place some monitors on the table, and so on. Such histories are totally missing in the video. You only have the results. So videos gives you all the real world changes, all the experience, even if you have taken some actions into the results. And the images, you have to go for some human-made artifacts like masking or some distillation from the teachers or so on to artificially create such changes or processes. Like from some visible patches, you predict some invisible patches or the global embedding and so on. Those are artificial changes, and many of them are not real world and even reverse of the real changes. So we expect video give us more real world changes that we can do better modeling later.
I see.
Have more comments?
No, I see the idea. So you want to explore the temporal dynamics. Yeah. I see. That makes sense. Thank you.
Okay, then I think so. We will wrap this up here. If nobody has any more queries, and we'll give. Yeah, yeah, sure.
So yeah, thanks for the talk, by the way. So I'm not very familiar with like vision pre-training. So I was just wondering if like how much of this CLIP or like MetaCLIP 1 and 2 covers like abstract concepts in visual images, such as like being healthy or being energetic, things like that, like things that are like not objects, like not necessarily localizable in the images, but kind of implicit. Because I'm kind of interested in downstream tasks, like trying to understand the evoke emotions or rhetorics or things like that. But I've been kind of testing like multimodal LLMs for these tasks, and I think they are kind of bit difficult for those models to do. So I was just wondering if like this has to do with like upstream, like these image encoders that are in those models. So I was just if like you happen to know how well those are covered in the pre-training of image encoders.
Daniel, do you have some answer?
Yeah, so I think this is a great question. I think even for image or vision encoder pre-training, it has a different type of the models. For example, like Dino is a pure SSL, and all the information is based on images. And I think the use case you just mentioned, I think it probably needs some kind of abstract concepts. And I think that's probably the benefit we see for CLIP or paired data pre-training styles. That some of the abstract concept can come from the languages paired with the images. So we do see the potential of our models or data can benefit this kind of research. We just don't have enough expertise in this area, so we definitely see like possible collaborations over there.
I see. Thank you.
And to also comment, I feel it can also be a future bottlenecks to learn those abstract concepts, even though MetaCLIP covers those concepts that the vision modality alone may not have enough real-world correspondence, and scaling the cross-model inference and so on could be the new bottleneck, which is, for example, if you have some web pages and some images, and later human language gradually generalize from what they see to what they saw, how those abstract concepts are built up, that can be important surrounding context. And currently such scaling is probably broken at the data collection stage, right? Which could be a new bottleneck, human-made data collection bottleneck. Yeah.
Thank you, for your excellent presentation, and Daniel for answering the queries as well. I hope we can talk to you later at your next presentation, new reps, or anywhere else. And you guys can reach the authors there on their LinkedIn, Twitter, or directly via mail. So they will be happy to answer your queries.
Mm-hmm.
Yeah.
Thanks so much for the invitation.
Yeah. Thank you so much.
Thank you. Bye. Take care.
Take care.